Gravity is a prison. It is an invisible, relentless warden that dictates exactly how far we are allowed to go, and the price of escape is almost impossibly steep. Every gram of metal, every breath of oxygen, every drop of propellant we try to push into the void requires an exponential sacrifice of energy. This is the tyrant known as the rocket equation. It states, with cold mathematical certainty, that to carry more fuel, you need more fuel to carry that fuel. It is a vicious, compounding cycle that has trapped humanity in the shallow waters of low Earth orbit for half a century. We look at the distant shorelines of the Moon and Mars, dreaming of permanent harbors, but our ships always run dry before the journey truly begins. To break this cycle, we cannot simply build bigger rockets. We have already reached the practical limits of what brute force can achieve against the curvature of space-time. The only way out is to fundamentally rewrite the architecture of space travel. We must sever our dependency on the surface, but doing so requires mastering a technology so delicate, so fraught with catastrophic risk, that it has never been attempted on a massive scale. It requires us to tame cryogenic fluids, oceans of super-chilled liquid methane and oxygen. In the absolute hostility of a vacuum, imagine trying to carefully pour boiling water from one fragile glass to another while in freefall, plummeting down an elevator shaft in pitch darkness. Now replace the water with volatile liquids resting at hundreds of degrees below zero, and the elevator shaft with the silent, irradiated void of deep space. In this environment, heat is a deadly infection. Sunlight is a weapon that boils propellant into pressurized gas, threatening to tear metallic bulkheads apart from the inside. Without gravity to settle the liquids, they slosh and float like violent, unpredictable phantoms within their tanks. There is a Leviathan waiting on the launch pad, designed to conquer this exact nightmare. A steel beast built to ferry humanity into the deep black, but its immense power is entirely useless unless we can solve the terrifying physics of orbital refueling. If we fail, the beast starves in the dark, and we remain prisoners on this rock. If we succeed, the solar system cracks open. The darkness of the cosmos holds secrets that demand to be understood, but the toll for that knowledge is paid in brilliant engineering and calculated risk. If you seek the truth hidden in the void and wish to comprehend the brutal mechanics of our expanding frontier, subscribe and join us on this journey. We are about to step into the cold. We are creatures of dirt and gravity. Every instinct we possess, every intuitive leap our brains make about how the physical world operates, was forged at the bottom of a heavy atmospheric ocean. When we throw a stone, it arcs and falls. When we pour water, it spills downward. When we run out of fuel on a long highway, we simply pull over, stop the engine, and fill the tank. It is an effortless, mundane transaction. Because of this, when we look up at the black canvas of the night sky, we naively project these terrestrial mechanics onto the void. We imagine space as just another ocean to cross, another highway to drive. We assume that if a spacecraft needs more fuel to reach Mars, we can just park it in orbit, send up a tanker, and pump the gas. But the cosmos does not care about our intuition. The moment you cross the Kármán line and enter the vacuum, common sense becomes a fatal liability. The rules of engagement are entirely rewritten by an invisible, unyielding grid of physical laws. Imagine wandering through a sprawling, hypermodern metropolis at 3 in the morning. The streets are entirely empty, dead quiet, devoid of any visible barriers. Yet, every traffic light still turns red. Every automated security grid tracks your movement, and every invisible sensor enforces a rigid, inescapable set of rules. The city appears open and free, but it is actually a tightly controlled machine. This is orbital mechanics. The void looks empty, but it is saturated with the heavy, invisible gears of gravity and momentum. You cannot simply pull over and stop. In orbit, there is no stopping. To stop is to fall back into the atmosphere and burn. To stay in orbit, you must maintain a relentless, agonizing state of perpetual freefall, traveling at 28,000 kilometers per hour just to continually miss the curvature of the Earth. Within this high-speed, invisible machinery, we are forced to confront the absolute tyranny of the Tsiolkovsky rocket equation. Long before the first steel was cut for any rocket, a deaf Russian schoolteacher named Konstantin Tsiolkovsky sat in a snowbound cabin in the late 19th century, armed with nothing but cold calculus and an obsessive gaze directed at the stars. He mathematically proved that the universe has erected a towering, almost insurmountable barrier to deep space exploration. The equation he derived is a statement of compounding cosmic debt. It dictates that every single gram of mass you wish to accelerate into the dark requires a specific, non-negotiable amount of propellant, but that propellant itself has mass. Therefore, you must add more propellant to lift the propellant that is lifting your payload. It is a vicious, diminishing return. It is why our rockets are not ships. They are flying fuel tanks. Over 90% of a rocket's mass on the launch pad is nothing but violent chemical energy, destined to be burned away in the first few agonizing minutes of flight, just to barely push a tiny sliver of metal into low Earth orbit. By the time a modern spacecraft reaches the vacuum, it is exhausted. It has spent nearly everything it had simply to escape the warden's immediate grasp. The tanks are nearly hollow. If you want to go to the moon or push onward to the desolate plains of Mars, you cannot do it with the fumes left over from launch. You need fully loaded tanks. The mathematical conclusion is inescapable. You must launch your empty ship, and then you must launch a fleet of tanker ships to meet it in the void. You must transfer the blood of the mission from one vessel to another, while both hurl through the vacuum at 22 times the speed of sound. On paper, our brains tell us this is merely a plumbing problem. We have been performing mid-air refueling with military fighter jets for decades. Two jets match speed in the sky, a boom connects, pumps engage, and jet fuel flows smoothly from the tanker to the receiver. But air-to-air refueling relies on the very forces that the vacuum of space strips away. In the atmosphere, gravity pulls the fuel to the bottom of the tank, where pumps can easily swallow it. The dense air provides aerodynamic stability. The ambient temperature, while cold, is manageable and relatively stable. In the abyss of space, every single one of these comforting terrestrial crutches is violently kicked away. First, we must dismantle the illusion of the cold vacuum. Popular culture has ingrained in us the idea that space is a freezing, icy domain. This is a fundamental misunderstanding of thermodynamics. Space is not cold. Space is nothing. It is a void, largely devoid of the atoms and molecules that give temperature a physical meaning. Heat is the vibration of particles. Where there are no particles, there is no temperature to measure. Therefore, a vacuum acts as an absolute, perfect insulator. If you place a spacecraft in orbit, it does not instantly freeze. Instead, it is subjected to a terrifying thermodynamic extreme. On the side facing the sun, unfiltered, brutal solar radiation bombards the hull. Without an atmosphere to scatter the energy, the metal bakes, absorbing immense amounts of thermal radiation. It is like leaving a sealed, black thermos on the asphalt in the middle of a blazing desert afternoon. The heat has nowhere to go. On the dark side of the spacecraft, facing the infinite black, heat slowly radiates away into the void, plunging the metal to hundreds of degrees below zero. The ship is simultaneously on fire and freezing, trapped in a relentless thermal war. Now, place thousands of tons of cryogenic propellant inside this volatile thermos. The lifeblood of the modern deep space architecture is liquid oxygen and liquid methane. These are not docile fluids like water or jet fuel. They are angry, hypervolatile gases that have been crushed into a liquid state through extreme, punishing cold. Liquid methane must be kept below -161 degrees Celsius. Liquid oxygen requires -183 degrees. At room temperature, they want to expand, they want to boil, they want to become a gas. When the sun's radiation strikes the hull of our orbital tanker, that heat slowly bleeds through the insulation and into the cryogenic tanks. The moment the heat touches the super-chilled liquid, the propellant begins to boil. It vaporizes. As it turns into gas, it expands massively in volume. The pressure inside the tank begins to rise. The metal bulkheads, strong enough to withstand the forces of launch, begin to groan under the internal strain of the expanding vapor. If you do not relieve this pressure, the tank will eventually rupture, turning a multi-billion-dollar spacecraft into a shrapnel cloud traveling at orbital velocity. To save the ship, you must open a valve and vent the boiling gas into space. But every time you vent, you are bleeding away the very fuel you spent a fortune in treasure and engineering to bring to orbit. It is a race against time. The sun is constantly boiling away your mission. But heat is only the first antagonist in this nightmare. The true horror reveals itself when you actually attempt to move the liquid from the tanker to the receiving ship. Because you are in free fall, there is no up and no down. Gravity has abandoned you. Without gravity to pull the heavy liquid to the bottom of the tank and hold the lighter pressurizing gas at the top, the fundamental architecture of fluid dynamics collapses. The liquid no longer behaves like a liquid as we understand it. Driven by capillary action and surface tension, the cryogenic propellant creeps up the metallic walls of the tank. It clings to the sides, forming a hollow, ghostly cylinder of freezing fluid. Or worse, the slightest vibration, the smallest thruster firing, causes the liquid to break apart. It forms massive, floating, trembling spheres of sub-zero methane and oxygen that bounce and collide within the dark cavern of the tank. The liquid and the gaseous vapor above it become entangled. The gas, known as ullage, no longer sits neatly at the top of the tank. It becomes trapped in massive, floating bubbles within the creeping liquid, or the liquid surrounds the gas entirely, forming a hollow sphere of fluid suspended in the center of the tank. Scientists have observed this behavior for decades. During the Apollo missions, engineers were terrified of what would happen to the liquid hydrogen fuel when the Saturn V's third stage had to reignite in orbit to push the astronauts toward the moon. They knew that if the engine tried to pull fuel and instead sucked in a gulp of gaseous hydrogen, the turbopumps would overspeed in a fraction of a second, tearing the engine apart and stranding the crew in Earth orbit. Later, aboard the International Space Station, meticulous experiments were conducted. Spheres of liquid were injected into transparent tanks and filmed in microgravity. The footage is haunting. The fluids do not slosh, they undulate, they form strange, pulsing geometry. When subjected to the slightest vibration, they shatter into thousands of smaller droplets, floating like a swarm of insects, before slowly coalescing back into a crawling, gelatinous mass. Now, multiply that behavior by 1,000,000. You are not dealing with a small plastic sphere on a space station. You are dealing with hundreds of tons of hypervolatile, boiling liquid inside a 50-meter steel silo. And this silo is not in a stable environment. It is subjected to the relentless 90-minute cycle of low Earth orbit. For 45 minutes, the docked ships plunge into the freezing shadow of the Earth. The metal hull contracts. The heat radiates away into the absolute zero of the void. The liquid inside the tanks cools and condenses. Then, abruptly, they cross the terminator line. They are thrust back into the blinding, unfiltered glare of the sun. The solar radiation hammers the steel. The hull expands rapidly, groaning under the thermal shock. The heat seeps into the cryogenic tanks, and the dormant liquid instantly begins to boil along the walls. This thermal cycling creates violent, unpredictable currents within the crawling fluid. It is called thermal stratification. Pockets of warm, boiling liquid mix chaotically with pockets of supercooled liquid. The pressure inside the tank spikes. The venting valves must open, exhaling precious propellant into space to prevent the tank from bursting. We are faced with an engineering paradox of staggering proportions. We have a tanker full of liquid that is clinging to the walls, boiling in the sunlight, and acting like an unpredictable, shape-shifting entity. And we need to forcefully move this entity through a narrow pipe, across the docking interface, and into the empty tanks of the receiving ship. We already know that mechanical pumps are useless in this environment. Cavitation will destroy the impellers the moment they ingest a mixture of liquid and gas. So, how do we force the liquid out? The theoretical answer is both brilliantly simple and horrifyingly complex in practice. If gravity has abandoned us, we must manufacture our own gravity. We must create an artificial acceleration vector. In aerospace engineering, this concept is called settling the propellants. If we want the liquid to fall to the bottom of the tank, where the transfer pipes are located, we must fire small thrusters on the docked ships. We must gently accelerate the entire massive structure in a forward direction. By accelerating the ship, the liquid inside, due to its immense inertia, will be forced to the rear of the tank, just as you are pushed back into your seat when a car accelerates. This is the microgravity equivalent of tapping a syringe to get the air bubbles to the top before an injection. But we are not tapping a small plastic tube. We are attempting to accelerate thousands of tons of metal and volatile liquid moving at 28,000 kilometers per hour. The amount of thrust required is a delicate, razor-thin margin. If you fire the settling thrusters too softly, the acceleration is not strong enough to overcome the surface tension of the creeping liquid. The fluid remains stuck to the walls, ignoring the artificial gravity. If you fire the thrusters too hard, the sudden jolt of acceleration will cause the massive volume of liquid to slam against the bottom bulkhead. This phenomenon is known as a fluid hammer. The sheer kinetic energy of hundreds of tons of liquid crashing into the base of the tank can warp the steel, shatter internal sensors, or violently destabilize the docked ships, causing them to tumble uncontrollably out of their orbital trajectory. We must find the exact mathematical sweet spot. We must apply a continuous, ultra-precise milli-g acceleration, just enough thrust to gently coax the crawling fluid down the walls and pull it over the transfer valves. but not enough to cause a violent slosh. But remember, these are two massive ships, physically clamped together. When you fire thrusters on one end to accelerate the entire structure, you are placing immense structural torque on the docking collar. The metal rings connecting the two ships are the only things preventing them from ripping apart. They must withstand the sheer forces of the acceleration while maintaining a perfectly hermetic seal for the cryogenic transfer pipes. One microscopic fracture in the seal, 1 millimeter of misalignment under the stress of the thrust, and the pressurized liquid methane will spray out into the vacuum. Even if we perfectly execute this artificial gravity maneuver, even if we settle the fluid into a neat pool at the bottom of the tank without snapping the docking clamps, we still have to push the liquid from one ship to the other. Without a mechanical pump, the only way to move the fluid is through pressure differential. We must pressurize the tanker tank and depressurize the receiving tank. We must inject a high-pressure, inert gas, usually helium or heated autogenous gas, into the top of the tanker. This pressurized gas acts like an invisible pneumatic piston. It presses down on the pool of liquid propellant, forcing it out through the pipes, across the delicate docking interface, and into the empty ship. But here, the laws of thermodynamics return to punish us once again. When you inject hot, high-pressure gas into a tank of supercooled, cryogenic liquid, the two substances interact violently at the boundary layer. The heat from the pressurizing gas immediately begins to transfer into the liquid pool, causing the surface to boil and vaporize. The pressurized gas itself begins to cool and collapse, losing its ability to push the fluid. The invisible piston begins to melt away. You are in a race against thermodynamics. You must push the liquid fast enough to complete the transfer before the pressurized gas collapses, and the liquid boils into a chaotic foam. But if you push the liquid too fast, the velocity of the fluid rushing through the narrow transfer pipes will create immense friction. In the frictionless void of space, this internal friction generates heat. That heat bleeds into the cryogenic fluid, passing through the pipes, causing it to flash boil mid-transfer. A pipe designed to carry dense liquid is suddenly choked with expanding high-pressure gas. The flow stutters, stalls, and violently reverses. The pressure spikes tear through the plumbing. The transfer fails. Every single variable is fighting against the objective. Surface tension traps the fluid. Thermal radiation boils it. Acceleration threatens to shatter the ships. Pressure differential collapses the system. The mathematics of fluid dynamics in microgravity are a labyrinth of diminishing returns and catastrophic thresholds. We are attempting to conduct heavy, volatile, industrial plumbing in an environment that systematically dismantles the physical laws upon which plumbing relies. The sheer scale of this undertaking cannot be overstated. We are not just trying to prove a scientific curiosity. The entire future of human expansion into the solar system balances on a knife's edge in this exact process. If we cannot master the dark, chaotic fluid dynamics inside those freezing steel silos, we are not going to Mars. We are not going back to the moon. We are trapped in low Earth orbit, staring at a horizon we can never touch, tethered forever by the tyrannical arithmetic of the rocket equation. The Leviathan on the launch pad may possess enough thrust to shake the Earth and shatter the sky, but its ultimate success relies entirely on a silent, microscopic war being fought inside its own dark belly, a war of temperatures, pressures, and unseen molecular forces. The engineers look at the telemetry, crunch the thermodynamic variables, and attempt to model the chaos. But a model is just a shadow of reality. The void is not a simulation. It is a harsh, unforgiving judge that demands absolute perfection. And as we push closer to the day of the first massive orbital transfer, a singular, terrifying reality begins to materialize in the equations. We are attempting to force the universe to yield to our ambitions, but the universe does not yield. It only waits for us to make a mistake, and the margins for error are shrinking to zero. We are approaching a physical barrier that cannot simply be engineered away with thicker steel or more powerful thrusters. We are walking directly into a fundamental paradox of deep space architecture, a contradiction that threatens to unravel the entire paradigm of interplanetary travel before it even truly begins. We are standing at the threshold of what systems engineers refer to as a deeply coupled problem. In the sterile, air-conditioned rooms where deep space architectures are drafted, a coupled problem is spoken of with a quiet, lingering dread. It means that every single solution you invent mathematically triggers a new, completely separate catastrophe in another part of the system. You cannot isolate a variable. You pull on one thread, and the entire fabric of the mission begins to unravel. The transfer of cryogenic propellant in microgravity is not a single engineering hurdle. It is a nested sequence of physical impossibilities, a labyrinth where every exit leads back to the center. To grasp the true nature of this barrier, we must look at the exact mechanism we intend to use to move the liquid. As we established, mechanical pumps will inevitably tear themselves apart through cavitation, and utilizing an external pressurized gas like helium introduces a massive weight penalty that the rocket equation will not tolerate. Therefore, the architects of this grand endeavor have turned to a concept known as autogenous pressurization. The premise is deeply elegant on paper, yet mathematically terrifying in practice. Autogenous means self-generating. Instead of bringing a separate gas to act as our pneumatic piston, we use the propellant itself. The ship takes a small portion of its own subcooled liquid methane, routes it through a heat exchanger attached to the roaring engines, and flashes it into a searing, high-pressure gas. This hot methane vapor is then injected back into the top of the propellant tank. Because it is gas, it expands. Because it expands, it creates pressure. It pushes down on the cold liquid below, forcing it through the transfer pipes. We are using the fuel to push the fuel. It is a closed loop, eliminating the need for heavy helium tanks, theoretically satisfying the ruthless demands of Konstantin Tsiolkovsky. But the universe despises a closed loop. The moment that hot, high-pressure methane gas enters the freezing, dark cavern of the tank and makes contact with the subcooled liquid propellant, a brutal thermodynamic conflict is initiated. We must understand the boundary layer. This is the microscopic, invisible horizon where the hot gas physically touches the freezing liquid. At this interface, the laws of thermodynamics dictate an immediate, violent transfer of energy. The heat from the gas rushes into the liquid, desperate to reach equilibrium. As the gas loses its heat, it loses its energy, and it begins to condense. It turns back into a liquid. The invisible piston we just created begins to melt, collapsing under its own thermodynamic weight. The pressure drops. The transfer of propellant stutters and slows. To prevent the transfer from stopping completely, the ship's computers must react instantly. They must siphon more liquid, flash it into more hot gas, and inject it into the tank to replace the gas that just collapsed. But here is the fatal paradox. By continuously injecting hot gas to maintain the pressure, you are constantly dumping thermal energy into a tank of cryogenic fluid that requires absolute, undisturbed cold to survive. You are essentially trying to build a bridge out of ice while continuously breathing fire across its surface to keep it suspended. As this thermal energy bleeds deeper into the liquid pool, the overall temperature of the propellant begins to rise. We are walking a razor-thin tightrope defined by the Clausius-Clapeyron relation, a mathematical equation that dictates the absolute threshold where a liquid boils into a vapor based on temperature and pressure. If the bulk temperature of the liquid methane rises by even a few degrees, it crosses the threshold. The liquid begins to boil from within. It flashes into vapor inside the transfer pipes. The flow reverses, slamming shut with the force of a fluid hammer, and the transfer violently aborts. You have effectively choked the beast with its own blood. To combat this, you might theorize that we simply need to cool the liquid while we transfer it. We introduce a technology known as active thermal control, or zero boil-off systems. We install massive cryocoolers onto the orbital depot ships. These are essentially spacefaring refrigerators, utilizing reverse Brayton cycles to actively pump heat out of the cryogenic tanks and radiate it into the infinite blackness of space. If we can keep the liquid artificially chilled, the hot, pressurizing gas will not cause it to boil. But once again, the warden of gravity steps out from the shadows. Cryocoolers are physical machines. They are composed of heavy compressors, sprawling networks of coolant loops, and vast external radiators. More critically, they require an immense, continuous supply of electrical power to operate. To generate that power, the ship must deploy massive, heavy solar arrays. Do you see the trap closing? You need a cryocooler to keep the fuel liquid. You need heavy solar panels to run the cryocooler. You have just added tons of dry mass to your spacecraft. And what does the rocket equation dictate when you add mass? It demands more fuel to push that mass. But if you need more fuel, you need larger tanks. Larger tanks have more surface area exposed to the sun, which means they absorb more heat, which means you need a larger cryocooler, which requires larger solar panels, which adds even more mass. It is an inescapable, spiraling feedback loop of mathematical doom. Every attempt to solve the thermodynamic problem invokes the wrath of the mass penalty, dragging the ship's efficiency down until it can barely escape Earth's gravity, let alone reach the desolate plains of Mars. The engineers are trapped in an endless negotiation with the laws of physics, and physics refuses to compromise. And yet, thermodynamics is only half of the barrier. If we assume, for a brief theoretical moment, that we can perfectly balance the temperatures and pressures, we must then confront the sheer kinetic horror of what happens when we actually begin to move the mass. We are not transferring water from a garden hose. We are moving 1,200 metric tons of mass from one vehicle to another, while both vehicles are flying through a vacuum at 28,000 kilometers per hour. To understand the danger, we must look at the concept of the moment of inertia and the ship's center of mass. Imagine a tightrope walker holding a long balancing pole. As long as the weight is perfectly distributed, the walker remains stable. But imagine if the weights on the ends of the pole were hollow spheres filled with water, and suddenly, the water began to rush from the left sphere to the right sphere. The center of mass shifts violently. The tightrope walker is instantly thrown off balance and plummets. Two massive starships, docked end-to-end, create a structure over 100 meters long, a towering steel skyscraper in orbit. Before the transfer begins, the tanker ship is heavy, and the receiving ship is light. The center of mass is located deep within the tanker. As the valves open and the subcooled liquid begins to flow across the docking interface, hundreds of tons of mass are actively migrating down the length of the structure. The center of mass is literally moving in real time. A spacecraft maintains its orientation in orbit using a reaction control system, a network of tiny, precise thrusters that fire in short bursts to keep the ship pointing at the sun or maintaining its trajectory. The computers calculating these thruster firings rely on algorithms that assume a fixed center of mass, but the mass is no longer fixed. It is flowing, it is sloshing, it is crawling up the walls. When the ship attempts to correct its orientation, it fires a thruster to pivot the structure. But the 1,000 tons of liquid inside does not immediately pivot with the steel hull. Because of inertia, the fluid lags behind. It washes up against the inner wall of the tank. A fraction of a second later, the immense weight of the liquid crashes against the steel, imparting its own counterforce against the ship. The ship's sensors detect this unexpected movement and command the thrusters to fire again in the opposite direction to compensate. This creates a terrifying phenomenon known as a harmonic resonance, or a slosh feedback loop. The fluid moves left, the thrusters push right. The fluid violently rebounds to the right. The thrusters aggressively push left. Like a massive, uncontrollable pendulum trapped inside a falling clock, the shifting liquid begins to actively fight the flight computers. In the vacuum of space, there is no aerodynamic drag to dampen this oscillation. The swinging amplifies with every second. The structural torque on the docking collar, the fragile metal ring holding the two massive ships together, multiplies exponentially. The computers are flying blind. To stop the resonance, they would need to perfectly predict the exact motion of a chaotic, boiling fluid in microgravity, but mathematically predicting fluid dynamics requires solving the Navier-Stokes equations. These are a set of partial differential equations that describe the motion of viscous fluid substances. They are so complex, so highly nonlinear, that solving them in real time for a chaotic, massive volume of boiling cryogenics is beyond the processing power of any flight computer currently in existence. The ship cannot calculate what the fluid is going to do. It can only react, usually too late. If the slosh feedback loop is not instantly recognized and forcefully dampened, the two ships will begin to wildly pitch and tumble out of control. The structural limits of the docking interface will be exceeded. The metal clamps will violently shear under the thousands of tons of torque. The ships will rip apart in a silent, blinding explosion of depressurizing methane and oxygen, scattering a cloud of frozen shrapnel across the orbital plane. To prevent this, the transfer must be agonizingly slow, meticulously controlled, and constantly paused to allow the fluid to settle. But remember the first paradox. We cannot pause. The sun is constantly baking the hull. The hot pressurizing gas is constantly melting into the liquid. The longer the transfer takes, the more the propellant boils away, and the more likely the entire thermodynamic house of cards is to collapse. We are forced to rush to outrun the heat, while simultaneously forced to crawl to outrun the kinetic instability. It is a perfect, inescapable contradiction. And lurking beneath all of this high-level physics is a silent, microscopic killer that haunts every deep space mission: the physical failure of materials. In our terrestrial lives, if a valve gets stuck, we apply lubricant, or we tap it with a hammer. In the abyss, a stuck valve is a death sentence. The mechanical plumbing required to execute this transfer is staggering. There are dozens of automated high-pressure valves, disconnects, and fluid couplings. These mechanical parts are subjected to a brutal, agonizing environment. First, they must survive the violent vibrations and acoustic shock waves of the launch. Then, they are plunged into the freezing vacuum, chilling to -180 degrees Celsius. At these temperatures, the atomic structure of materials fundamentally alters. Teflon seals shatter like fragile glass. Stainless steel contracts, changing its microscopic dimensions, causing tight-fitting parts to seize. But the most insidious threat is a phenomenon known as vacuum cementing or cold welding. On Earth, every piece of metal is coated in a microscopic layer of oxidation, a thin film created by the oxygen in our atmosphere. This layer acts as an invisible barrier, preventing the raw atoms of two pieces of metal from ever truly touching. In the hard, oxygen-starved vacuum of space, this protective layer can be scrubbed away by mechanical friction. If two pieces of polished steel inside a transfer valve slide against each other without that oxide layer, their raw atoms come into direct contact. Because they are in a vacuum, there is nothing to tell the atoms that they belong to two separate pieces of metal. The electrons begin to share orbits. In a terrifying instant, the two separate pieces of steel fuse together on an atomic level. They do not just stick, they become a single, solid block of metal. Imagine a robotic valve deep inside the dark plumbing of the orbital depot, commanded to close in order to stop the flow of high-pressure liquid methane. The steel gate slides shut, but the friction strips the oxidation. The valve cold welds to its housing. The computer registers an error. The valve is stuck open. There is no astronaut outside with a wrench to fix it. There is no atmospheric pressure to aid in breaking the seal. The liquid methane continues to surge through the pipes, completely out of control. The receiving tank fills, reaches capacity, and the pressure begins to skyrocket. The venting systems try to compensate, screaming precious propellant into the void, but the flow is too fast. The internal pressure of the giant steel silo breaches the structural limits of the metallurgy. The telemetry screens in a control room, thousands of miles below, show a sudden, catastrophic drop in pressure across all sensors, followed by a total loss of signal. We possess the blueprints to build the ships. We possess the engines to throw them into the dark. But between us and the rest of the solar system lies this invisible, chaotic barrier of thermodynamics, fluid mechanics, and atomic betrayal. It is a wall made not of stone, but of boiling methane, creeping frost, and mathematical paradoxes. We are demanding that a chaotic, volatile substance behave with absolute, rigid precision in an environment designed to strip away all control. Every time the engineers close a loophole in the physics, the universe opens to more. The mathematics spiral endlessly, pointing toward a terrifying conclusion about our place in the cosmos and the sheer arrogance of our attempts to leave our atmospheric cradle. We have been raised on a diet of generational optimism. We look at the wooden caravels that crossed the Atlantic, the steel locomotives that conquered continents, and we intuitively project that same manifest destiny onto the stars. We view the cosmos as the ultimate frontier, an open ocean waiting for our sails. But the agonizing failure to easily move a simple cryogenic liquid in the dark reveals a much more restrictive truth about our reality. Space is not an ocean, it is a quarantine zone. The physical laws of fluid dynamics, thermal radiation, and atomic friction that we are violently colliding against are not mere engineering hurdles. They are the invisible bars of a cosmic cage. By making the act of storing and transferring potential energy so infinitesimally complex, the universe has built an isolation ward around every gravity well. We are permitted to build lenses that capture the ancient light of galaxies burning billions of light years away. But the mechanics of the void seem explicitly designed to ensure that while we can see the infinite, we are physically forbidden from touching it. The barrier of orbital refueling exposes the fatal flaw in our vision of becoming a multiplanetary species. If it requires 15 flawless, high-velocity rendezvous missions, perfectly choreographed artificial gravity maneuvers, and the suppression of chaotic fluid dynamics just to get one single ship out of Earth's shadow, then the entire architecture of human expansion is built on a mathematical knife edge. To conquer this quarantine, we build more complex machines. We introduce autogenous pressurization, active cryocoolers, automated docking clamps, and dense networks of thermodynamic sensors. Each system is a marvel of intellect, but every microvalve added to the ship is a loaded gun pointed directly at the mission. In statistical mathematics, this is a series system reliability model. If a ship relies on 10,000 critical components, and every component has a 99.9% chance of surviving, the overall probability of the ship surviving plummets exponentially. The math multiplies the risk with every new moving part. In the terrestrial world, a broken pump means you stop and repair it. In the abyss, a broken pump means the crew suffocates in the dark or burns in a depressurizing explosion. We are demanding that volatile chemicals behave perfectly in an environment where ambient temperature swings by hundreds of degrees in minutes. This reveals a chilling possibility about the Fermi paradox, the lingering question of why we have never heard a whisper from anyone else in the cosmos. We usually imagine the Great Filter as something spectacular. We imagine nuclear annihilation, rogue artificial intelligence, or engineered pandemics. But what if the Great Filter is entirely mundane? What if it is not a war, but a valve? What if the universe is silent because the physics of deep space logistics are simply too unforgiving? Perhaps thousands of civilizations have reached the edge of their atmospheres, built their leviathans of steel, and slowly realized that the energy cost, the thermal constraints, and the uncontrollable fluid dynamics of moving propellant in a vacuum are a statistical dead end. The Great Filter might just be the grinding impossibility of maintaining complex industrial supply chains in a void that aggressively punishes complexity. They didn't blow themselves up. They simply ran the numbers, realized the cage was locked from the outside by thermodynamics, and quietly turned their backs to the stars. And if we somehow force the lock, if we bleed enough treasure to brute force the cryogenic transfers and push a fully fueled ship out of Earth orbit, we are immediately confronted with the next hidden consequence of our mass dependency, the terrifying distortion of time. Because we are so restricted by the mass of our propellant, we cannot travel in straight lines. We cannot simply point the nose of the ship at Mars and ignite the engines. The rocket equation forbids it. We are forced to bow to orbital mechanics, coasting along the slow gravitational contours of the solar system, utilizing the gravity of the planets to pull us along like driftwood. This means we do not dictate the schedule of our expansion. The celestial clockwork dictates it. Earth and Mars only align for a fuel-efficient transfer once every 26 months. If you miss that window by a few days, or if a single cryogenic transfer valve freezes shut during refueling and delays the launch, you do not wait a week for the next flight. You wait 2 full years. Time itself becomes the ultimate enemy. A journey to Mars, relying on these hyperefficient trajectories, takes anywhere from 7 to 9 months. 7 months, trapped inside a metal cylinder, entirely dependent on machines operating at the absolute razor edge of material science. If a solar flare erupts, or if a micrometeorite pierces the thermal shielding of the propellant tanks, there is no quick return. There is no turning the ship around. Once the engines have burned and the deep space propellant is exhausted, you are locked into the orbital curve. You will reach your destination in 7 months, whether you arrive as pioneers or as a tomb of frozen ghosts. This is the existential terror of the distances involved. We have shrunk our own planet to the size of a glowing screen in our hands, accustomed to instant communication. But out there, the scale of the void shatters our perception of time and consequence. When a ship reaches the orbit of Mars, a radio transmission, traveling at the absolute speed limit of the universe, takes up to 22 minutes just to cross the gulf of space and reach Earth. Imagine being a crew member aboard that distant ship. A klaxon sounds in the dark. A telemetry sensor indicates that the pressure in the cryogenic methane tank is rising dangerously fast. A haunting ghost of the very same thermal dynamics that nearly destroyed the ship in Earth orbit. You transmit an urgent plea for help to Mission Control. You send the data. You ask for the mathematical solution to save your life. And then you wait. You sit in the humming silence of the ship, watching the pressure gauge climb, listening to the agonizing emptiness of the void. For 22 minutes, your message crawls across the barren expanse of the solar system. For 22 minutes, the engineers on Earth do not even know you are dying. When they finally receive the signal, they scramble, formulate a desperate command code to bypass the failing valve, and transmit the fix into the black. And you wait another 22 minutes for the answer to return. 44 minutes of absolute, crushing isolation. In a thermodynamic scenario where cryogenic systems can critically fail and rupture a steel hull in milliseconds, 44 minutes is an eternity. It is a death sentence delivered by the fundamental speed limit of reality. The sheer latency of the universe becomes a suffocating blanket. In that silence, you realize that you are not just millions of miles away. You are locked in the past, completely severed from the temporal flow of the human race. This is what the silent struggle with cryogenic propellant truly represents. It is a stark, unforgiving redefinition of our place in the cosmic order. We are not the masters of physics. We are its fragile hostages. The roaring Leviathan on the launch pad is not a symbol of our dominion over nature. It is a towering testament to how much violence, fire, and unfathomable engineering we must invoke just to cross the threshold of our own atmosphere. Every time a massive steel ship vents its boiling gases into the vacuum, it is a visceral reminder that we are fighting a war of attrition against an enemy that does not sleep, does not age, and does not negotiate. We are forced to confront a reality that decades of science fiction have meticulously hidden from us. The future of human space travel is not elegant warp drives and sleek, brightly lit corridors. It is industrial grunge. It is massive, freezing pipes groaning under immense pressure. It is chaotic, unpredictable, fluid dynamics that constantly threaten to tear ships apart. It is human engineers staring at screens, sweating in the pale glow of telemetry, knowing that a single line of bad code or a microscopic flaw in a Teflon seal will result in the silent, instantaneous vaporization of everything they have built. Our desire to conquer the dark is driven by an ancient, evolutionary imperative to survive by reaching the next horizon. But the hidden consequence of this endeavor is the crushing realization that the universe has already factored our biology into its equations. It has explicitly designed the spaces between the worlds to be the ultimate antithesis of our existence. To venture into the deep black is to willingly walk into a thermodynamic meat grinder. It requires a terrifying embrace of cold, ruthless mathematics to build self-sustaining ecosystems floating in an ocean of nothingness that actively wants to reduce them to dust. We are attempting to build a permanent empire in a graveyard. We stare at the night sky and see a canvas of infinite promise, a frontier waiting to be tamed. But the void is not a promise, it is a warning. The universe is not a waiting room for our ambitions. It is a sprawling, indifferent, self-correcting machine. And we are the anomaly, a fragile, carbon-based glitch born at the bottom of a gravity well, attempting to actively rewrite the operating system of the cosmos. The barrier we face is not simply a matter of engineering. It is a confrontation with the fundamental architecture of reality. The boiling fluids, the creeping surface tension, the structural agony of artificial gravity. These are not merely mechanical problems to be solved in a sterile laboratory. They are the physical manifestations of the universe rejecting our presence. We are attempting to force a volatile, atmospheric chemistry to operate flawlessly in a domain where that chemistry is meant to remain frozen, silent, and entirely dormant. Yet, despite the impossible mathematics, the Leviathan still waits on the launch pad. It stands there venting white plumes of vapor into the terrestrial sky, a towering monument to our sheer, terrifying audacity. We will eventually launch our massive steel ships. We will watch them pierce the atmosphere, trailing pillars of fire, carrying the immense weight of our relentless biological need to exist beyond this rock. And up there, suspended over the blue curvature of our only home, in the silent, irradiated darkness, the invisible war will begin. The docking clamps will violently engage. The mechanical valves will open. The subcooled fluids will meet the vacuum. The atomic structures of our greatest machines will grind against the absolute limits of their physical reality. It will be an agonizing struggle of thermodynamics and pressure, hidden entirely from our view, masked perfectly by the deafening silence of orbit. Perhaps human intellect will prevail. Perhaps we will mathematically force the physics to yield, inch by agonizing inch, perfectly calculating the microscopic accelerations and the thermal decay. We might successfully transfer the lifeblood of our ships across the abyss, bleeding our resources dry to forge a fragile, pressurized bridge of steel across the dark. The sheer scale of the cosmos reduces our greatest industrial achievements to microscopic static. Yet, when the engineers on Earth hold their breath, waiting for the telemetry to confirm the flow of liquid methane, they are participating in a brilliant, desperate rebellion against the overwhelming entropy of the universe. But we must thoroughly understand what that victory actually means. Even if we completely succeed, even if the beast is perfectly refueled, ignites its engines, and pushes out into the deep black toward the rusted, dead plains of Mars, it changes absolutely nothing about our true standing in the dark. We are not conquering the void. You cannot conquer an entity that does not even acknowledge your existence. We are merely learning how to survive a fraction of a second longer within its jaws. We are building thicker armor, more intricate plumbing, more desperate illusions of control, all while plunging deeper into an environment that mathematically dictates we should not be there. The cosmos will not applaud our engineering. It will not care that we mastered the boiling, chaotic ghosts inside those freezing tanks. It will simply continue to expand, infinitely cold, infinitely dark, waiting for the inevitable moment when the engines finally stop burning, and the heat fades away entirely.